Yeah, does it work?
Yeah.
Perfect. Okay, great. So I'm gonna discuss some things related to black holes in flat holography. So there will be some sort of very broad, vague statements, and then some very concrete, specific statements regarding to the topics that Andy didn't get to in his talk on Monday regarding the photon ring. So, I think most of the work in this field has sort of focused on taking Mellon transforms of perturbative scattering amplitudes, which is, obviously the right place to start because that's the piece of data that we have. But our goal is really to do flat space holography, and holography is really a non-perturbative gravitational phenomenon. So, really most of the arguments for holography in quantum gravity come from black hole physics. But I think that really black holes haven't been integrated in any fundamental or really meaningful way in the celestial CFT formalism so far. So, really, if the goal of this field is to construct some holographic dual to gravity in flat space, nobody is going to really believe that we succeeded if we can't describe Schwarzschild and Kerr. So I think it's really important that we actually start thinking about that problem because black holes really play the fundamental role in really most holographic dualities that we know and love. But I think it's a little bit mysterious what role they should play in flat holography for a couple of reasons. So the first is that, in Schwarzschild ADS, so the large black holes in anti-de Sitter space, we know that they're basically approximately thermal states. So, they're high energy eigenstates, they have chaotic properties, which are basically guaranteed by these conjectures about eigenstate thermalization. But as has been kind of pointed out a couple of times already at this conference, we don't really have a well understood map in flat space between the states of the bulk Hilbert space and states in this Euclidean CFT dual that we use to compute scattering amplitudes. So it's not really clear what the analog of this statement would even be in flat space. So I think it's actually just a very important question to try to understand, what does e to the s Bekenstein-Hawking mean in celestial conformal field theory? Similarly, what does the black hole temperature mean? And what do the chaotic properties of horizons mean in celestial conformal field theory? As far as I know, this has really not even been touched or considered in the literature, and I think it's a really important problem. Now, because black holes in asymptotically flat space are just qualitatively different than the ones in anti-de Sitter space, it could be that their role is just completely different, and we can't use any of the intuition that we gain from anti-de Sitter space. And if that's the case, coupled with the fact that black holes play such an important role in holography, it might just be that all the formalism has to be significantly different from that of anti-de Sitter space. Yeah, so just kind of, and this is the sort of conclusion of the vague things that I want to and please also, it should be an informal discussion, so interrupt me and actually interact with me. But I just want to say, the thermodynamics of black holes in flat space is very different than the thermodynamics of black holes in anti-de Sitter space. So these ones, they're thermally stable. They have good thermodynamic properties, the black holes in flat space, like Schwarzschild, they have negative specific heat, they have a super Hagedorn density of states. It's pretty hard to imagine constructing a local field theory with those bad properties. So it's a little bit confusing what they should be. It could be that, that E to the S Bekenstein-Hawking is density of states for resonances in CFT correlators. So in other words, in flat space, black holes are all sort of just very long-lived resonances. So it could be that, you know, this information is just built into properties of this celestial conformal field theory correlation function in terms of resonances, which, you know, if you know basically how these long-lived resonances behave, then maybe you can say something interesting about these correlation functions. Hasn't really been done, but it would be interesting to try. And one kind of concrete problem in this direction is a paper by Polchinski called Chaos in the Black Hole S Matrix. Where he basically writes down a formula that looks a lot like a soft theorem or a Ward identity for scattering in a black hole background. So basically, the cartoon of what he shows is that if you have, you know, a black hole horizon and some scattering process defined on it, and you add an extra particle, which drops into the horizon, well, by the time it reaches the horizon, it's super blue shifted, acts like a shock wave. So if there are other particles which are sort of traveling near the horizon, eventually making it out to scry, they will receive a time delay. So sort of adding a particle to the S matrix looks like doing a time delay on states at scry, but what else does time delay at scry? It's super translation, right? So he's written down a formula that looks a lot like it relates an insertion of a particle in the S matrix to an action of super translation on external states. And I think this is something where the variables that we are used to using appear very naturally in the black hole context, and it might be interesting to kind of try to understand this in celestial CFT. Yeah. Yeah. Yeah, so I mean, there's one calculation that you can do, which would just be the S matrix on a black hole background with non-dynamical gravity, and then I think then that calculation is probably exact in some sense. If we actually have dynamical gravity, then you know, you have to figure out how to phrase this in terms of a very long-lived resonance, right? So as you say, the black hole won't exist forever, but I mean, heuristically, you know, like if I shoot something at the black hole at the center of our galaxy, the black hole is going to be around for a while, right? So you should probably be able to get some type of physical statement out of it, yeah. But it is more complicated.
And sorry, again, a very naive question. The modeling of the ingoing bit of the scalar in, so you need to be at a small impact parameter when you're hitting it with these other things to really follow the shock wave?
Yeah, so, well, yeah, they need to interact in the near horizon region
Right, so
in some way.
I mean, because I have photons and they interact with the scalar far away from the black hole, so there's nothing.
Yeah, no.
Seems like there's some regime.
Yeah, you need to aim the particle so that it actually falls in the black hole, right? So if, you know, if you have the black hole and you just shoot a particle out here, obviously that's not going to have this effect. You need to take some wave packet where it actually is going into the black hole, and then if there's other stuff moving sort of out towards scry and they interact, then you'll get this effect. Yeah. So it's not exactly like the soft theorems, but it has a similar flavor, and I think that's what's interesting about it. Okay, so now I'll just switch gears and tell you something sort of very specific about black holes in flat space, which is related to this paper that we wrote a couple of months ago. The title is a little bit provocative, but it's called Holography of the Photon Ring. Okay. This was with Alex Lipchaska, Shahar Hadar, and Andy Strominger. And this paper is interesting for a couple of reasons, in my opinion. The first is that it's actually going to be relevant for experiments that will happen in our lifetimes, especially the very long baseline interferometry experiments that are actually taking pictures of black holes. But the formulas in this paper are actually also relevant for any proposed quantum mechanical dual to asymptotically flat black holes like the ones in the center of our galaxy. So that's kind of the aspect that I'm going to discuss here. So just to kind of remind you and set the stage, and as a little piece of motivation, sort of in the usual decoupling limit, which is really the only way that we know how to describe near-extremal black holes, you have some system of strings and branes, and that system has some interesting geometric transitions, so that a weak coupling is described by strings and branes, and a strong coupling is described by a black hole. And you take basically a low energy limit to decouple the open strings from the closed strings, and the analog of taking a low energy limit for the black hole is going to the near horizon region, right? Because that's where all of the redshift is. So basically what the usual decoupling limit, which leads to ADS CFT in the throat of the near extremal black hole, what it tells you is that if you have some black system, whether it's black holes or black branes, for low energy probes coming from an outside observer, the black hole behaves as if it was just a non-gravitational system. So the response of the black hole to low energy probes is just that of some quantum field theory, some non-gravitational quantum field theory, which you can sort of think of as living at this boundary of the ADS throat, which to an outside observer looks like it's sitting right on the degenerate horizon, right? So we sort of think of the black hole as its near horizon ADS throat, and we can replace that region with the quantum mechanics, and that's the basic result of gauge gravity duality. So really the thing that near extremality buys for us in this case is a clean separation from the black hole system and the far region, right? And it basically allows you to put the holographic screen for the black hole right near the horizon, because you have this huge throat which looks like it's all scrunched up right near the black hole. But the point is that we don't have that separation for non-extremal black holes, right? You just don't have a huge throat for the Schwarzschild black hole or for a spinning black hole far from extremality. And so you want to know where do the E to the S states in that system, if they're actually supposed to be described microscopically, where do they reside? And it's kind of a confusing question. I don't think there's any known answer to it, this paper is kind of trying to gather some evidence for what the answer might be. Okay, so just as sort of a cartoon for what's happening, if you imagine that you have some well-defined Hamiltonian for quantum gravity in asymptotically flat space, you know, there's some piece which, roughly speaking, associated to the black hole that probably has some discrete spectrum, e to the s states. You know, there's some Hamiltonian for the far region, and then there's some interaction term that couples the black hole to the far region, right? And in the extremal black hole case, where you go to sort of zero energy and you zoom in on this region of space-time, you basically can ignore this interaction term. The black hole is decoupling from the far region, and you can just forget about the far region and just study the black hole Hamiltonian in the throat. And that's basically supposed to be the Hamiltonian for the quantum mechanics described by the strings and branes. But far from extremality, you really can't ignore this term. And in particular, you know, you probably remember that if you have a system with a discrete spectrum and then you couple it to something with a continuous spectrum and then turn on an interaction, discrete spectrum just becomes resonances, right? So it's sort of very different type of system when you're far from extremality. Okay, so, you know, we can think of this old decoupling limit as sort of, we don't usually think about it this way, but you could think about it as a limit in phase space. So we sort of go to the near horizon region in configuration space, and we go to the low energy region in momentum space. Now, in this example, these are kind of redundant limits because the horizon has all of the redshifts, so going close to it is the same as going to the low energy part of phase space. But we don't always have this region of the geometry, this huge infinite volume throat. So what we did in this paper is actually to define a new scaling limit for non-extremal black holes, which turns out to actually still have some interesting universal features. So whereas the old decoupling scaling limit, which has kind of been paying the bills for 25 years, you go near horizon and low energy, this new scaling limit that we defined, you go what I'll call near ring and actually high energy or high frequency, okay? So it's a very different scaling limit than the usual one. And in particular, you're actually scaling in on a region which can be several Schwarzschild radii outside of the black hole. It's called the photon ring, and it's basically the region in the space-time where all of the bound null geodesics live. So the place where the photons just orbit infinitely long, get trapped by the black hole. Well, so this is just a definition of a scaling limit. I haven't told you why it's interesting. The reason it's going to be interesting is because it's going to connect the geometry of the photon ring to the spectrum of Ruel resonances of the black hole, okay? So at a calculational level, what it does is connect the geometry of the photon ring to the spectrum of quasi-normal modes. But the point is that in every example of holography for black holes that we know, spectrum of quasi-normal modes gets mapped to the spectrum of Ruel resonances, which are basically the damped oscillations of slightly perturbed thermal state, right? And it's basically this scaling limit which is going to relate that spectrum, which has sort of a nice, clean quantum mechanical interpretation to things about the geometry, which are universal and controlled by the space of geodesics in the black hole geometry. Well, I mean, the interesting fact about holographic systems is that it basically turns classical statements about gravity into quantum mechanical statements in the dual, right? Well, yeah. What I'm assuming is that for a general black hole, even far from extremality, that it has some description as a quantum mechanical system. We don't know that 100%. We know it for sure in anti-de Sitter space. And we have what I would say is pretty strong hints from black hole thermodynamics, even in asymptotically flat space. Right? So for many purposes, you can treat, you can forget about the black hole and just treat it as some analog system which has response to perturbations. And probably the membrane paradigm is the best known example. But I think it's a pretty safe assumption. Yeah, so I mean basically that the Kerr black hole will be some density matrix that has a temperature and some, angular potential, and I'll calculate 2-point functions in this black hole geometry, and I'd like to interpret those as 2-point functions in some non-gravitational system. And the exponents in that 2-point function are what I'm going to call Ruel exponents. So you can just do a purely gravitational calculation. You'll get an answer. There will be exponents controlled by the quasi-normal modes. If we assume that holography applies to asymptotically flat black holes, which if it doesn't, then basically this whole conference is moot, then if we assume that, then they will be interpreted as Ruel resonances in the dual quantum mechanical system. Yeah. Yeah, and well, I don't know if it's a definition. What Ruel resonances have an independent definition. The question is whether or not the black hole has a quantum mechanical dual or not. Yeah, it's just the state of the black hole. Well, it could be a pure state that looks approximately thermal. That's the way it looks in ADS, right? Well, that's what, no, there's no really well-defined boundary of the throat when you're far from extremality. That's kind of the point. So what we're gonna sort of show in this paper is that there's a certain amount of information which is contained on this very interesting time-like surface, which is the photon ring. More generally, it should be thought of as a surface in phase space, not just in space-time. And some of the information about the black hole, for instance, its spectrum of shortwave Ruel resonances is controlled by this region out here. That doesn't mean that is the holographic plate for the black hole. We don't know if that answer even has a well-defined question, but it's at least a candidate, and it does control some very important aspects of the black hole dynamics. Yeah. I'm not sure of any alternate characterization in terms of an extremization problem. There might be, but really the definition is most straightforward just in terms of it's the space of bound null geodesics in the geometry. So, I mean, we're kind of headed in that direction anyway, but, why could it be that this thing has any actual information about the black hole when it is several Schwarzschild radii away from the horizon? Well, the first fact is that if you imagine a star collapsing on itself to form a black hole, before it passes through its Schwarzschild radius, it will pass through its photon ring. Generically, it will radiate into the photon ring. And those are basically the longest geodesics in the space-time. So the radiation gets stuck there, goes around for a very long time, very slowly leaks out towards asymptotic observers. So really, actually, the last light that you see from the black hole is along this photon ring, the image of the photon ring on your screen. And because it's not sitting right at the horizon, it's actually not as redshifted as the dark star when it passed through its event horizon. So that's sort of one very cartoonish motivation for why there might be information about the black hole there. But I think more importantly for this paper, if you smack a black hole, its response is basically controlled by that region of the geometry. You can think of the quasi-normal modes, which are the relaxation to equilibrium, basically just as waves leaking off of the photon ring. Yeah, go ahead. Yeah, I mean, there are some debates about that, but I think it's pretty safe to say that they'll need a telescope in space if they want to see what. The moon would be great. I don't think that they'll get that, but orbiting Earth, it might be doable. I think there's some momentum for that. The diffeomorphisms which preserve the photon ring. Well, that's the. Well, I think the invariant. Okay. Well, there are a couple of different questions. The first question would be whether or not this is actually a diffeomorphism invariant statement. That I think is true. You can just think about this as the space of bound null geodesics. So we could do some diffeomorphism on the radial coordinate. And these might not all be constant radius geodesics anymore, but they'll all still be bound to the black hole. They won't reach scry. A question of whether or not you could treat this as like a boundary and understand if there was some group of diffeomorphisms that preserved it. I haven't thought about that. I don't really know. Yeah, so something interesting happens actually. So in the near extremal limit, actually the photon ring moves into the throat region. At least part of it does, not all of it. Some of the, so for Kerr, there's actually a band of radii where you can have bound null geodesics. Part of it moves into the throat region. And actually, if you make a plot of what the, so I'm going to plot two things here. One is basically the dispersion relation for the quasi-normal modes for Kerr. What it will do is something like this. So it becomes linear past some angular momentum. That linearity is basically a signal of the emergent SL2 symmetry in the throat. All of these other photon ring geodesics stay out of the throat, so they don't have that property. And if you look at what happens to the Lyapunov exponents, so the imaginary parts of the quasi-normal modes, they there's some very complicated expression in terms of elliptic functions, and then it goes to zero for the ones that move into the throat. The interpretation of that fact is that you can have a wave now which bounces around for a very long time in this semi-infinite throat, so it has a very long lifetime, and the imaginary part of the quasi-normal mode controls the lifetime. So yeah, the fact that the photon ring moves into the throat in the extremal limit and is actually responsible for the linear dispersion relation in the quasi-normal modes in something like an ADS3 throat is, I think, another hint that it can be related to the black hole system. Yeah, so the quantity that we're at, well, let me just write it down. Oh, I see. Yeah, so I'll first explain the gravitational calculation that we're doing, and then I'll say how it's supposed to be interpreted, right? So, gravitational calculation that you do, so we would like to eventually view the black hole as some approximately thermal state, right? So we're interested in, basically, you have some black hole, you hit it, and you study what it does. What is its response to the perturbation? I'm going to do linear response theory on the black hole. when you hit a black hole, there's usually sort of 3 different phases of the response. So there's an initial prompt response, which depends on the explicit details of what you threw into the black hole. You know, it could have been 2 black holes that collided, or you just threw in a particle. The prompt response is not universal. Then there is a sort of linearized regime where the kind of final black hole is more or less emerged and it's just trying to shed its remaining hair and settle down to equilibrium. That's the quasi-normal mode phase. And then there's a much longer time scale related to backscattering off of the Coulomb tail, and that's related to price tails, which I'm not going to discuss. But in the quasi-normal mode ringing phase, you're basically just trying to solve a massless wave equation, but with non-Hermitian boundary conditions. So what do I mean by that? Well, okay. Most of the black holes in 4 dimensions have a separable wave equation. So if we try to plot the radial potential in tortoise coordinates, potential usually looks something like this. And quasi-normal mode boundary condition just means that it's going into the horizon and out towards spatial infinity, right? Okay, so this is, you know, second order differential equation. We're imposing 2 boundary conditions, so we're likely to get a discrete spectrum, but because we're imposing non-Hermitian boundary conditions, we actually get complex spectrum, right? So this is the thing that you're trying to compute gravitationally. You just want to know the solutions to this equation in the black hole background with this boundary condition. Now, usually we can't solve that equation exactly. Really, and, you know, there's some 3-dimensional examples, there's hypergeometric functions, but beyond that, you really can't solve the spectrum exactly. There's only a particular limit of this equation which we know how to handle analytically, and that's the short wave limit, right? Or the iconal approximation. So there we sort of assume that we have an ansatz for the field in terms of some rapidly varying phase and a slowly varying amplitude. And there's usually a very useful quantity, which is just the gradient of the phase. And if you take this ansatz and you plug it into this equation and just write out what you get, I want to get the coefficient correct. Give me a sec. Yeah. Okay, so that was just basically a change of variables, but the shortwave approximation means that I try to solve this order by order in powers of p, right? So at first order, you will just find that p has to be a null geodesic and that it satisfies the massless geodesic equation. So now we know that we're going to be building solutions using geodesics in the geometry. And then we have to impose the boundary condition, and it turns out that this boundary condition corresponding to quasi-normal modes basically requires that you use geodesic congruences that are on the photon ring. So in other words, that are bound to the black hole, equivalently that they have a double zero in the radial potential. Okay? And then the second order basically tells you that the transport of that amplitude along the congruence is just controlled by the expansion of that congruence. So in particular, if you have an expansion with positive, if you have a congruence with positive expansion, which is like the photon ring because they're unstably bound null geodesics, then you'll get exponential decay according to how much expansion that you have. And this expansion is always basically related to the Lyapunov exponent of the photon ring trajectories, okay? So this is the calculation that you're doing on the gravity side. It's just the short wave approximation to the wave equation. and we basically writing solutions in some asymptotic series in terms of geodesics, okay? Is that clear? Yeah. Okay. So okay, so lesson one is that the shortwave part of the quasi-normal mode spectrum is controlled by the photon ring. Okay, in other words, the decay of the waves, which is related to the Lyapunov exponents of the photon ring, which is the same as the imaginary parts, yeah, of the quasi-normal mode frequencies. Right. Now, so the answer to the second part of your question is we would like to interpret these quantities in the event that the black hole is describable as a state in a non-gravitational quantum mechanical system, right? So in that event, like imagine that you were in anti-de Sitter space for a moment and you have some black hole sitting in the middle of it. The quantity which is related to Ruel exponents is the thermal two-point function, right? So you want to sort of calculate some two-point function at different times. Okay, so like, you know, operator 1 is a function of T1, operator 2 is a function of T2 at some inverse temperature beta. And this thing will be some, you know, sums of exponentials. Okay, there's other kinematic dependence, but the important part is these damped exponentials, right? So, you know, the way that this type of calculation arises in the near extremal case is if you're sitting out here with a near extremal black hole and you send in some perturbation at some early time that's like replacing that perturbation with some operator at the boundary of the throat, letting it propagate and interact in the throat, and then come back in, back out at some later time, right? So you measure this two-point function in an approximately thermal state, and you observe that it has these damped Ruel exponents, right? Now, this is a calculation which you do using classical gravity. The point is that it has an interpretation in terms of a quantum mechanical two-point function because we know we can replace the black hole with the non-gravitational system, right? So the assumption really that we're making is that even when it's not near extremal, that you can sort of find some, you know, some holographic plate for the black hole where you can sort of forget about the fact that it's a black hole and calculate response non-gravitationally, right? That's exactly what you do for near extremal black holes where you replace the throat, which is ADS, some dimensionality, with a conformal field theory. If holography works for black holes in asymptotically flat spacetime, which is an open question, but we think probably the answer is yes, then we think you should be able to replace the black hole in some sense with non-gravitational system, and then the Ruel exponents of that non-gravitational system would be fixed by the photon ring. Is that clear? Well, I'm trying to describe for you the part of the paper which is relevant to flat space holography workshop. And there I think the statement which nobody has made in the past, because I think people really think mainly about ADS black holes. So there's a statement which we think will be true in gravity and asymptotically flat spacetime, which is the classical Lyapunov exponents are equal to quantum Ruel exponents. So this is really thought of as a constraint on possible duals to the Kerr black hole. In other words, so for instance, this scaling limit is not the scaling limit that you would do for Schwarzschild ADS. Actually, that spectrum of resonances is completely different than the spectrum of resonances for an asymptotically flat black hole. So it's kind of a challenge for theorists to find some quantum mechanical system which has that, you know, particular dispersion relation instead of Ruel resonances that correspond to Kerr. Basically, all that has ever been done is to reproduce this approximately linear piece in the event that the black hole is near extremal. So it's sort of a diagnostic for the types of non-gravitational systems that could potentially be dual to a Kerr black hole. Most non-gravitational systems will not have this spectrum of Ruel resonances, basically because in this case, the spectrum of resonances is geometrizing itself in terms of some geometry outside of the black hole horizon. Most quantum systems won't have that type of spectrum because they have nothing to do with the photon ring. So this part of the discussion, which is only about half of the paper, but is the most relevant to holography, is basically kind of reinterpreting some results, whose I think we kind of improved the technical discussion in the case of Kerr, but you reinterpret those formulas as a constraint on possible quantum mechanical duals for the Kerr black hole. Well, these are interpreted basically. They also arise as poles of the S matrix on the black hole background. That's another way to phrase them. Yeah, so that's an interesting question. It would be interesting to know like what the celestial CFT of the quasi-normal mode spectrum is. Well, I mean, it might be difficult because this is not a boost eigenstate. You're breaking symmetry with the black hole. There's still an S matrix. You might be able to do something interesting. I think it's an interesting problem. I just haven't really thought how to do the calculation. Sorry? Oh, yeah. So there's another part of the paper which I'm not discussing here, which relates to the actual black hole images. So basically, the photon ring, if you think about it in terms of what these experimentalists actually observe, you know, general relativity basically predicts that there's this infinite sequence of nested subrings, basically an infinite number of images of everything that you see. And basically how it works is that the demagnification factors between successive subrings are given basically exactly by these Lyapunov exponents. And it turns out that if you study the phase space of an integrable system like the geodesic problem on Schwarzschild, it's actually possible almost always, at least locally, to construct an SL2 action, which what it basically does when you have a fixed point like the photon ring is to drive all of the points in this image towards the ring, okay? So that's sort of a continuous action on phase space, and there's a discrete subgroup which basically maps one subring to the next according to this Lyapunov exponent dilation factor. It's much more complicated in Kerr because there's a whole range of exponents, but in Schwarzschild, this is what it does. And there's also sort of an emergent SL2 symmetry in the quasi-normal mode problem. We're kind of used to there being emergent symmetries when you take very particular scaling limits in black hole geometries. I didn't tell you, but the quasi-normal mode spectrum, it usually comes in overtone families. So you'll have some real part associated to the photon ring orbit and some fundamental imaginary part related to the Lyapunov exponent. And then you'll have sort of an infinite family of them, each of which decays more and more quickly. And in cases where we can solve this equation exactly, like the three-dimensional black holes, this overtone number is always related to the descendant level in an SL2R symmetry. So obviously, most black holes in higher dimensions, far from extremality, don't have a geometrically realized SL2R symmetry. But it seems that there is some sort of emergent SL2 symmetry in phase space in this particular limit where you go to high frequencies in the near ring region that relates the different overtones in terms of descendants. We don't really understand the relation between these two emergent scaling symmetries yet. We sort of struggled for a while with it and didn't manage to really nail it, but we're still thinking about it. Well, you see, you could have expected that they should be related because I've built solutions to the wave equation using geodesics. So if I have an action on geodesics, there should be a way to translate that into an action on the wave equation. But it is a little bit more complicated. We didn't manage to really nail it. Right? Well, there's an easy way to see the existence of the overtones just from geometric optics. So let me explain that to you because it does relate to SL2 symmetry. So this transport equation, you can see that if you have a solution, well, if you have some quantity which is parallel transported along the which is basically conserved along the congruence, then if A0 was a solution to the wave equation, then, you know, L minus to the n will also be an approximate solution to the wave equation, right? Now, there's kind of two ways to find solutions to this equation. The first is if you have a killing vector, in which case, you know, L dot P, you know, is conserved along a geodesic. And in the examples where we can solve the wave equation exactly, there always is an SL2 symmetry. And that's why the overtone number in those cases is related to the descendant number. So the kind of, you know, what's happening in these examples without the explicitly realized symmetry is that you can basically solve this equation kinematically. So because these are unstably bound geodesics, which means that if you perturb them a little bit, they shoot off exponentially quick. So the radial deviation from the ring grows exponentially. So if you solve e to the minus gamma t delta r, that's approximately conserved on the photon ring. So you can actually use that to build up solutions giving us seed solutions. And those are precisely the overtone wave functions in the near ring region. And the point is just that this is exactly the function that you get from L dot P in the cases where there are exact SL2 symmetries. So what it looks like is there's sort of this emergent algebra of SL2 functions near the ring responsible for the overtone function, but which does not extend geometrically to the whole space-time. That's the idea.
Cool. All right. Well, that sort of formally ends today's session. We'll see everyone bright and early tomorrow morning. Kenny.